Good afternoon and Assalamualaikum. I am Sutiro, researcher in Department of Aeronautical and Electronics Engineering, National Formosa University, Taiwan. Now I will explain how to determine the operation region of NMOS circuit when we are presented by a specific circuit. So we want to analyze what is the operation regions that this NMOS experience in this circuit with following configuration. Uh, we know that the NMOS has three different operation regions. The first one is cutoff operation regions. This occurs when VGS less than VTN. VGS less than VTN. VGS is the voltage across the gate between the gate and source. Gate is here and source is here, while it is a drain. When the VGS is less than VTN, which is the threshold voltage, in this case we assume that the threshold voltage is 1.5 voltage. So the cutoff regions means the NMOS has no current flowing through its drain and source. So ID is equal to 0. Okay. The second one is triode region. In the triode region, the NMOS has the drain current can be expressed as mu n Cux W over L VGS minus VTN times VDS minus VDS square over 2, like this. In the case of channel length modulation is considered, we can add following part 1 over lambda VDS. But in this case, because we ignore the channel length modulation, so we can substitute lambda with 0, and we can simply ignore this part. The triode region occurs when NMOS following two requirements. The first one is VGS is greater than VTN, and the second one is VDS is less than VGS minus VTN. The VDS is voltage between drain and source. This is VDS, and this is VGS, like this. Okay, and the last one is the saturation region. The drain current can be expressed as a half mu n Cux W over L times VGS minus VTN square. The condition of saturation region occurs when VGS greater than VTN, while VDS greater than VGS minus VTN, like this one. Okay, from all of these three regions, we can evaluate the condition of NMOS in this circuit. Okay, the first one we want to examine is it in the cutoff region or not. So we will try to assume that NMOS is in the cutoff region. Then the implication must be VGS less than VTN. Otherwise, NMOS is not in the cutoff region. Okay. If VGS is less than VTN, then NMOS is in the cutoff region. But this is the implication. But if VGS is greater than VTN, it must be not in the cutoff region. So we need to calculate the VGS. VGS is equal to VG minus VS. The VG here Okay, before we calculate this, I want to remember that in the NMOS, there is no current flowing through the kit. So we can simply write as Ig is equal to 0. And here is Is, which is the source current flowing through the source. And this is Id, the drain current flowing through the drain, is equal. So Is can be written as Id, like this one. And from this one, Vg can be calculated using the voltage divider circuit. It can be written as Vg is equal to R1 over R1 plus R2 times VDD. And we get 10 mega ohm over 20 mega ohm times 15. So we get Vg is equal to 7.5 volt. While Vs, you can see in this circuit, Vs is actually equal to the voltage across the resistor R1. So we can write Vs as this is Rs, Rs times Id, like this. So we can write that Vgs is equal to 7.5 minus RSID. Rs is 1 kilo ohm, and we can write directly as Id. In this case, Id is in the milliampere. Okay, from this one, we need to evaluate is VGS less than VTN or not. We know that in the cutoff region, ID is equal to 0. So if we assume that NMOS is in the cutoff region, then ID must be equal to 0 based on this assumption. So by this assumption, we need to evaluate the implication of this. We get VGS is equal to 7.5 minus 0, it's equal to 7.5 volt. This is greater than 1.5 volt. This is a threshold voltage. So from this assumption, we get a contradiction between the assumption of cutoff, which is ID is equal to 0, with the reality that VGS is greater than VTN. This violates the requirement of cutoff region. Okay, so the first conclusion, not the final conclusion actually, the first conclusion is NMOS is not in the cutoff region. It can be in the triode region or saturation region, but we will examine under this. But in this case, first conclusion is NMOS is not in the cutoff region. Okay, so it can be in the triode or saturation. Next, we try to evaluate, is it in the triode or in the saturation region? Actually, we can firstly assume it is in the triode region according to this region, but we prefer to start with the assumption of saturation region because the formula of IT is simpler here rather than the triode region. You can see that in the saturation region, the IT only the function of the VGS, while in the triode region, IT is the function of both VGS and VDS. So we prefer to evaluate the saturation region if it is correct. So the NMOS must be in the saturation region, but if it violates the assumption, then it must be in the triode region directly. We start with this one. Okay. Okay, the next one is we assume that NMOS is in the saturation region. The saturation region. In this case, so the assumption is IT, we assume IT is equal to a half mu n cox w over L VGS minus VTN square will uh, will give the implication of VGS greater than VTN and VTS greater than VGS minus VTN, like this one. Okay, I will give a different value here. It must be more interesting if I give here like 4, maybe 4 kilo. From this, we can write directly, I think. We can write directly IT is equal to a half mu n cox is equal to 1.5 and times VGS is 7.5 minus IT minus 1.5 square. So we will get the 4 IT will equal to 3 times 6 minus IT square. 4 IT is equal to 36 minus 12 IT plus IT square. And we get 4 IT is equal to 108 minus 36 IT plus 3 IT square, and 3 IT square minus 36 IT plus 100x. Sorry, this one must be minus 50, minus 50, and we get IT is equal to, using algorithm formula, we get IT is 40 plus minus 1600 minus 4 times 3 times 100x over 2 times 3. So IT will be equal to 40 plus minus, it is sorry, times 3 6 9 over 6. So it will be equal to 40 plus minus 300 and 4 over 6. And IT we can use this one, I think. 40 plus square of 3 over 6, 9.57 milliampere, and in negative we get 3.75, 3.76, milliampere. Which one is correct? So we will evaluate the implication here. The implication here. We already get the IT. So the next step is evaluate the implication here. For VGS, for IT is equal to 9.57. We get that VGS is 77.5 minus IT is equal to 1.5 minus 1 kilo time minus, this is negative really negative. However, in the saturation region, VGS must be greater than VTN. This is 1.5. So VGS must be greater than 1.5. While in the value of IT equal to 9.57, we get that VGS is negative. So we don't need to continue the implication of the IT equal to 9.57 because there is one requirement was violated. So we can directly conclude that 9.57 is not correct answer. But it doesn't directly impact to be 3.76 milliampere to be a correct answer. It's not directly implied that. So we will need to evaluate this value also. The implication of this, we get that VGS is equal to 7.5 minus 1K times 3.76 milli. So we get 7.5 minus the 3.76. We get it's about 4. Okay. Or this is 5, 4, 7. This is 7, 3.75. 3.75 volt. This is satisfy the requirement. However, we still have another requirement, which is the VDS one. VDS one here. VDS must be greater than VGS minus VTN. Okay. VDS here can be written as here. VDS is voltage across the end source. So we can write VDS as VDD minus RDID minus RSID. So we can write again VDD minus RDID minus RSID, which is equal to 15 minus 4K ID minus 1K ID, or we can simplify by removing the K, and we remember that this is the IT in the milliampere. So we get 15 minus 4 minus 5 IT, like this one, 4 TS. So from this value, we will get that VDS will equal to 15 minus 5 times 3.7x, which is we know that 15 is equal to 5 times 3. So we can easily evaluate that this one is also negative because 3 minus 3.76 is negative. So although Although the VGS satisfy the requirement of the saturation region, however, the VTS violates the saturation region. Because if we compare the VGS minus VTN, VGS minus VTN must be 3.75 minus 1.5 must be 2.24 volt. And in the reality, VTS is negative, so it must be less than 2.24. So the assumption of NMOS is in the saturation region is failed also. So the conclusion is NMOS in the triode region. We practically don't need to prove the satisfaction of the NMOS requirement in the triode region, region requirements. We can stop our work until this one, and we can be confident to say that NMOS in the triode region. However, I want to show you that our conclusion is correct. So I will give you the bonus here by giving the proving that the NMOS is perfectly satisfy the triode region. And we remember that in the triode region, the ID is equal to mu n COX W over L times VGS minus VTN times VDS minus VDS square over 2 assume like this one. I think we don't need to assume this one because I'm confidently I confidently say that this is true, so I can write directly that fit ID will equal to 1.5 time VGS is the VGS is 7.5 minus IT minus 1.5 times VTS is 15 minus 5 IT minus 15 minus 5 IT square over 2. We can write 4 IT is equal to 3. 15 minus 80 minus 3, 15 minus 5 IT minus 15 minus 5 IT square, and we get 4 IT is equal to 3. This is 12 minus IT times 15 minus 5 IT minus 15 minus 5 IT square. 5 IT 3 we can put outside the 15 minus 5 IT part, and we leave the 12 minus IT minus 15 minus 5 IT here, and we get for IT is equal to 3 15 minus 5 IT, and this one is 12 minus 15 is minus 3 minus 80 plus 80 is 4 IT, like this one. We get 4 IT is equal to 3 minus 45 and plus 60 IT minus plus 15 IT minus minus 20 IT square, and we get here as 60 IT square, then 75 times 3 is minus 225 IT plus 4 IT and plus 225, sorry, 135 and plus 135 equal to 0, and we get, yes, this one, 80 square minus 221 IT plus 135 is equal to 0, and we can use al- algorithm equation. We get IT will be 2021 plus minus 2021 square minus 460 over 1120. Yeah, okay, yes. And we get using this most 20 221 minus 420. Okay, okay, 128 21 plus minus 120x point 2 over 120. So IT can be 20, 21, 221 plus over 2.9, 2.9 milliampere, and the second one is in the negative, is 1 is 0 0.77, 0.77 milliampere. So from this one we can check, uh, whether is satisfying the triode region. Is it 22.9 or 0.77? The first one is for IT is equal to 2.9 milliampere, and we know that the requirement of the triode region is VGS greater than VTN, while VTS is less than VGS minus VTN. Okay, VGS firstly is equal to 7.5 minus IT. It's equal to 7.5 minus 2.9 is equal to 4.6 volt, which is greater than 1.4. This is VTN. This first requirement is satisfied, but how about the VTS? VTS is 15 minus 5 IT, so we get 15 minus 5, 2.9. It's equal to 5, 3 minus 2.9, 0.5 volt, 0.5 volt, and VGS minus VTN, VGS minus VTN is equal to 4.6 minus 1.5 volt. to 3.1 volt. From this one, we can understand that 0.5 is less than 3.1 volt. So with this value 2.9 milliampere, we can confidently say that the NMOS in that circuit is in the triode region with drain current 2.9 milliampere. Well, how about the drain current 0.77? I confidently say that it must evaluate one or both requirement. We can evaluate it. For the first one, PGS must be equal to 7.5 minus 0.77, and we get this about 6.73, yeah, 6.73 volt, while the VTS must be 15 minus 580 and equal to 15 minus 5 times 0.77, which is equal to 15 minus 3.85, and it's equal to 11.15 volt. And when we compare VTS with VGS minus VTN, VGS minus VTN is 6.73 minus 1.5. It's equal to 5.23 volt. 5.23 volt. We can see that VTS is greater than VGS minus VTN. This is the requirement of the saturation. But the calculation is come from the triode region. So from this, we can conclude that this is this violet, but this satisfy. So the conclusion is NMOS is in the triode region with IT is equal to 2.9 milliampere. Why we have to determine the operation region of the NMOS? Because different operation region, their drain current has different equations. So if you use different equation, that then its operation region, it must be false. So you need to determine its operation region first, and prove that the drain current is correctly calculated. Thank you very much. Assalamualaikum.